This unit is really just a quick review and little touch on stuff that you learned back in algebra and how it applies to quantitative literacy in that how it applies to the real world. Okay, so that's what we're trying to do here. We're not trying to go really in depth into each of these subjects, just touching on them. So linear growth, it says we must begin our exploration of mathematical growth with a couple of questions. What is mathematical growth? And what does understanding growth matter? Why does understanding growth matter when understanding mathematics and the mathematical world we live in? To understand each of these questions, we need to first have an understanding of the growth in the context of mathematics. So whether you want to admit it or not, the world is a mathematical world. Everything in nature, everything that we do is governed by mathematics. And so understanding at least a snippet of that is something important to know. So we'll start with proportions. It's the relationship between quantities that vary at the same rate or varies directly with each other are known as proportions and can be written as linear functions. When two expressions are proportional, we say that there is a direct variation among the expressions. In other words, this means that as the value of one expression increases, the other value also increases. And the same thing, if one value decreases, the other also decreases. Jessica is interested in purchasing a new video game that costs $60. If she has a job that pays $7.50 per hour, find a linear equation for her income and determine the number of hours she must work in order to have enough money to pay the game. So we have her income, I'm going to call that I, and the number of hours she works. Let's call that H. And so which one would be the independent and the dependent? Well, her income depends on the number of hours she worked, right? So the number of hours she worked is our independent variable, and the income is dependent. So the income is $7.50 per hour. Every hour she works, it goes up by $7.50. So 1 hour would be $7.50. 2 hours would be $15, and so forth. Okay? And then it asks us how many hours would she have to work to get enough money to play by the game. Okay, let's see. She needed $60. So her income is going to need to be $60 for her to be able to buy this game. So we solve for H. Divide both sides by 750. And 60 divided by 7.5 is 8. She'll need to work 8 hours if she wants to purchase this game. The slope of a line is defined as the ratio of the change in the y values, the rise, divided by the change in the x values, the run, between 2 points. The slope of a line is defined by this formula. The slope, which we call m, is rise over run. It's the change in the y values over the change in the x values. Now you often see here the little formula y sub 2 minus y sub 1 over x sub 2 minus x sub 1. Yes, that is true. That is the way you find slope if you want to memorize a ridiculous little formula. The way I remember it is subtract the y's over subtract the x's. I just find that a little bit easier to remember because it's difference of the y's over the difference of the x's. Because change is difference or subtract. You just have to make sure you start both with the same point. The graph of a function that creates a line with a constant rate of change or slope is a linear function. Assume you have $20,000 in a bank account that you'll use to pay your college tuition. If the cost of your college tuition is $2,500 per semester, use a linear function to find the number of semesters it would take for the account to have a balance of 0. And assume that this bank account does not earn interest. So I guess it's a jar of money under your bed. So basically what we're trying to find out here is how many semesters can you go to school on $20,000. So we first want to set up our equation. So let's see. The amount in the account starts with $20,000. And every semester we subtract $2,500. So we're going to subtract off 2,500 times the number of semesters I'm going to call S. And so that's how we write our equation. Okay, we want to find out when that will be 0. So when will the amount in the account be 0? So we plug in 0 for A. And then we solve for S. So first, subtract 20,000 from both sides. And then divide both sides by negative 2,500. And negative 20,000 divided by negative 2,500 is 8. So you could attend school for 8 semesters on that $20,000. And here's a graph of that. You can see we started with 20,000, and each semester we went down 2,500. X and Y intercepts. The x-intercept is the point where the graph intersects the x-axis. And the y-intercept is where it intersects the y-axis. So if we look back at our picture here, we can see that y-intercept would be 0, 20,000. And the x-intercept would be 8, 0. Slope-intercept form is what we've been looking at, where we start with a value and then add a value times some number. That's y equals mx plus b. So b is the y-intercept. So if we look back here, our equation, let's get rid of some of this, was y equals 20,000 minus 2,500 S. B, it's just written in a different order, was 20,000. Okay? It's the y-intercept. And then M, your slope, is the number divided by S. So M would be negative 2,500 because we went down $2,500 in the account each semester. Example 3 says, assume Jeffrey has an uncle that puts away $10 in a shoebox on the day he's born and adds $5 to the shoebox on his birthday every year. If this trend continues, use a linear equation to find the amount of money in the shoebox on Jeffrey's 18th birthday. So, the amount in the shoebox starts with $10 and adds $5 every year. There we go. There's our equation. The y-intercept would be 10. The slope would be 5. And then it says, find the amount on his 18th birthday. So we would take this equation and plug in 18 for the number of years. There'd be $100 in the account on his 18th birthday. And that finishes up our section. Here's a little a graph here that you can see adding $5 each year. There's where there'd be 100 on his 18th birthday. On Desmos, we'll just look at, say, example 2. It said, where a baseball team wishes to purchase shirts for their team members and families. I just want to show you how to put this into Desmos. If you don't have a graphing calculator, this is a wonderful tool. And I'll continue to add these little videos on for the rest of the lesson, or the rest of the chapter. So we've got y equals 200 plus 12x. Oh, need zeros in there, huh? So now we've entered the function in, but you can see we can't see it. So all you got to do is scroll out. And it's aligned, so there we go. You can see right there. If we change the screen a bit, we said the domain would be all non-negative numbers of shirts. So if we go to graph settings, and we can change the x-axis from 0 because we're not looking at negatives. And I mean, we can put in anything here. I'll say 1,000. And then the y-axis, again, we don't want negative numbers, so we can start at 0, or we could start at 200 because we know that the price is going to start there. But so we can see it better, I'm going to start at 0. And I'll go to 1,000 again. Then we can click off. And so you can see your graph here. You can also plot points like we did on part C with this program if you like. All you got to do is input the points. So 0 to 100. And of course that one was already there. Then we had 5 to 60. And you can see where that's graphed now. And if you click on it, it'll tell you what the point is. And then we had 10, 320. So there's those 3 points on there so far. So just wanted to give you a little introduction to what you can do with Desmos with linear growth. So that was example 2 in section 5.1. And yeah, I mean, it'd be the same if we looked at example 2 in section 5.2. which is where I'll add this video onto. We can put y equals 20,000 minus 2,500x. And we would need to change our viewing window again, of course. So the y values need to go, this was a bank account, so from 0, and it started at 20,000. And the x values will go from 0 to, let's just say 10. And so here's our graph where we were losing money every semester. We were losing $2,500. Okay, so that's just an idea of how to use Desmos.